Okay, so we have just discussed how we extract information from standard form, how we convert standard form to some of the other forms if we need to. We need to talk about intercept form, take a little bit of a closer look at intercept form. So first of all, just to reiterate, here is intercept form, and just to make sure we're all understanding that in intercept form, pure intercept form, the coefficient in front of the x's is a positive 1. Occasionally you may see, in fact, I believe we'll see something like this in a example that is coming up. If you see something like 3x minus 1, let's say times negative x minus 4, this is not really intercept form. This is not truly intercept form. Yes, it is true that you can very quickly get your intercepts from this form by some of the strategies we talked about back on page 136. But in order to convert all of this into intercept form, we would need to factor the 3 out of this first factor, and we would need to factor a negative 1 out of the second factor in order to get this in pure intercept form. Right now, we would probably just call this factored form, a more a less specific form than intercept form, factored form where we have our two factors. And again, we can extract our zeros pretty quickly and easily from this form, but the zeros are not staring us in the face like they are in intercept form. Again, we'll see an example of how we go about converting something that's in that factored form into the more specific intercept form. So why is intercept form called intercept form? Well, remember, it is because the intercepts of the parabola, the x-intercepts, which are also the zeros of the quadratic, are staring us in the face, the p and the q, whatever's in the p position, whatever's in the q position. When we have a quadratic in intercept form, the p and the q are our intercepts. And by the way, if you do see a question that gives you, let's say the question gives you a quadratic in standard form and then says which of the following equivalent equations shows the x-intercepts of the parabola corresponding to this quadratic, well, most of the time you just need to go to the answer choices and pick the answer that is in intercept form. Conversely, if they give you intercept form and maybe they say something like which of the following shows you the y-intercept of the parabola corresponding to this equation, well, then you'd probably want to pick standard form. Mentioned that when we were going over extracting information from standard form as well. So let's go through all of the information that we can extract from intercept form. Of course, the easiest, most obvious thing, just mentioned this, are the zeros. We can get these zeros from intercept form. I am going to write down here x-intercepts. Remember that zeros and x-intercepts are synonymous, and the whole reason that we call intercept form is because we can see the x-intercepts. I do write here, see page 136 for the ways that we can extract the zeros from intercept form, but do keep in mind that if a quadratic is given in intercept form, then p and q are the x-intercepts. In other words, the points p comma 0 and q comma 0 are your x-intercepts. The y-intercept of the parabola you can find from intercept form in one of two ways. One, which we already talked about in standard form, we can set x equal to 0, because remember the y-intercept occurs when x equals 0. You have your y-intercept at 0 comma b. However, do keep in mind that that actually is really more for a linear equation in y equals mx plus b form. Remember, when it comes to a parabola, you can also convert your intercept form to standard form, and remember that the c hanging out there at the end of standard form will be the y-intercept. So your y-intercept will be at 0 comma c. Again, it doesn't really matter which way you go. You can either set x equal to 0, solve for y or f of x, or you can just FOIL out intercept form to get standard form, and then whatever is hanging out there at the end is going to be your y-intercept. So the y-intercept will occur at 0 comma c. I'm going to actually change that b to c there just so that we don't get confused. Orientation of the parabola, same as in standard form. No difference here. So if your a, which is this coefficient hanging out here in front of your factors, if your a is positive, if it's greater than 0, you have a opening upward orientation or a smiley face orientation, and your vertex is a minimum down there at the bottom of the parabola. And if a is less than 0, if a is negative, you have a downward facing or frowning orientation, meaning that your vertex is going to be a maximum. Now, speaking of the vertex, how do we get the x-coordinate of the vertex from intercept form? Well, again, there's multiple ways to do this, but one of the easiest ways is to find your zeros and then average them. We need to go into a little bit of detail about why that is. I'm going to do this down here. Let's say that you have zeros at, I don't know, let's say at -2 and 5. Okay, so maybe you have something like x plus 2 times x minus 5. Remember that x plus 2 is the same as x minus -2. And x minus 5 is obviously x minus 5. So you have your p there and your q there. Your p is -2, your q is positive 5. So we've got an intercept form quadratic right here. We know that this quadratic's parabola is going to intersect the x-axis at -2 and 5. We also know that parabolas are symmetric with respect to the vertical line that runs through the vertex. So there is some vertical line in between these 2 points. I'm going to put it here for now. We know that these 2 points, the -2, 0 and the 5, 0, need to be equidistant from that vertical line. That is what symmetrical means. Whatever this distance is to the left of that vertical line to the point -2, 0 must be the same distance as this distance to the right to the point 5, 0. So there is some vertical line that our vertex goes through, some x value where the vertex lies, that again will be arranged such that this distance and this distance are equal. Well, another way of saying that is that there is a midpoint of these 2 points, and at that midpoint will lie our vertex. And midpoints are exactly the same as averages. So if I were just on a regular old number line and I was looking at the points -2 and 5 on that number line, the way that I would find this midpoint is I would simply average -2 and 5. So I would do 5 plus -2 divided by 2. That's how I find the average of 2 numbers. Find the sum, divide by the number of numbers. And of course, this is going to be 3 halves. So my midpoint of these 2 points is positive 3 halves. So that vertical line, wow, I drew it pretty much right where it needs to be, so that's good. That vertical line has the equation x equals 3 halves, and that also means that my vertex, which is going to lie on that vertical line, is going to have an x-coordinate of 3 halves. Now, in order to find the y-coordinate, all I would do is take that 3 halves, I would take that average, and I would just plug that average into my function. So I would take 3 halves, I would plug 3 halves in here, plug 3 halves in here, calculate whatever this equals, and I would get my y-coordinate at the vertex. So again, to find the x-coordinate of the vertex, when I know my zeros, I just average the zeros. If I want the y-coordinate of the vertex, I just take the average of the zeros and evaluate the function at the average of the zeros. Let's take a look at number 26. We're going to go through a few examples here. If you want to try 26 on your own, you can pause the video. However, I do want to point out that this is that situation where we actually don't have pure intercept form. Now, that doesn't mean we can't find the roots and the y-intercept and so on and so forth, but there are 1 or 2 of these examples here that we have to be very careful of assuming certain things about the parabola if we don't have pure intercept form. So here's what I'm going to do. I'm going to convert the function as given to pure intercept form, and the way that I'm going to do that, I'm going to do that over here. So I'm going to factor a 2. So let me do this. I'm going to put that 3 out there in parentheses. I'm going to factor a 2 out of the first factor, this 2x minus 1, and what do I get? I get x minus 1 half. When I distribute that 2 back through, I can see that I'm going to get the 2x minus 1. So now there's a 2 out here. And then from this second factor here, I've got to factor out a negative 1 from that factor so that I end up with x plus 2. But remember, x plus 2 is the same as x minus negative 2. And now all of this stuff becomes negative 6. And then I have x minus 1 half. And then x minus, again, negative 2. And now I have pure intercept form where I can see that my zeros are p and q. So there's 1, 0, there's the other 0, and those, of course, are the intercepts of this parabola as well. So now my roots, I can just write 1 half and negative 2. 1 half and negative 2 are going to be the roots. Did I need to convert to pure intercept form to find my roots or my zeros? No, I didn't need to. Remember, I could also just use the zero product property to find the root associated with this first factor. So that's plus, why am I adding 2? I should be adding 1 there. Plus 1, I get 2x equals 1, divide by 2, and of course I get x equals 1 half. That's what I got over here. And then for this one over here, negative x minus 2, I'm going to use the zero product property there as well. So that's negative x equals positive 2, divide or multiply by negative 1, and I get x equals negative 2. So again, I can extract my roots or zeros from a quadratic that is in more general factored form, but I can see the zeros. I can physically see the zeros without having to do any algebra when my quadratic is in pure intercept form. Coordinates of the y-intercept, again, I can use either form. I could use the form over here, pure intercept form. I could use the form here, the more general factored form. I'm actually going to use the more general factored form here. The coordinates of the y-intercept, remember what we do is we evaluate the function at x equals 0, because that's where the y-intercept is on the y-axis, where all of my x's are 0. So I do 3 times 2 times 0 minus 1, and then minus 0 minus 2. So what does all this become? This becomes 3 times negative 1 times negative 2, and that all equals 6. So the coordinates of the y-intercept are 0, 6. Again, could have thrown the 0 in for the x over here, would have gotten exactly the same thing. Coordinates of the vertex. So remember how we find the coordinates of the vertex from factored or intercept form. We find our roots and then we average our roots. So what is this going to be? This is going to be the sum of the two roots that I found in 26a over 2, the number of roots. And I'm going to do this in my calculator. I don't want to mess this up. So calculator's coming up here. You can use your calculator here. It's perfectly fine. So I am going to do this the fancy schmancy way, and I'm going to use my alpha F1 menu so that I can get these fractions in here. So this is 1 half plus negative 2. I should put that in parentheses to be safe, but I'm living on the edge. So that is going to be negative 0.75. So I know my x coordinate at the vertex is negative 0.75. How do I find my y coordinate? I just plug that negative 0.75 into the function. So how do I want to do this? I'm going to do this with the store function. So I'm going to store that negative 0.75 in my x key, and I'm going to hit enter. So now x, this key has the value negative 0.75. So now what I'm going to do is 3 parentheses 2x minus 1 and parentheses negative x minus 2 and enter, and I get 9.375. I could also obviously write this as negative 3/4 comma. Let me convert this to a fraction, and I get 75 over 8. So the coordinates of the vertex are negative 3/4 comma 75 over 8, or of course you can use the decimal form there. Next, is the vertex a minimum or maximum? This is the example I was referring to where I said you got to be really careful to know whether you're looking at pure intercept form or just factored form. If you just look at factored form, it would appear that your a value is 3. But of course, in pure intercept form, we can see that our a value is not 3. Our a value is actually -6. And because our a value is -6, we know that this parabola has the down-facing or frowning orientation, which means that our vertex is a maximum. So that point right there at the very top of the parabola, the vertex, that point has those coordinates -3/4, comma 75.8, and we would also say that 75.8 is the maximum value of the p function. Remember that the p function and the y coordinate are synonymous. 75/8 is the maximum value of p. The equation of the axis of symmetry, well, that's easy. We've already found it, because remember, the equation of the axis of symmetry is the x coordinate at the vertex. So the axis of symmetry is this vertical line that runs through that vertex, and that equation of the axis of symmetry is going to be x equals -3/4 or x equals -0.75. So that is how we extract information from intercept form. Again, the one you really got to be careful of if you are trying to determine whether your parabola is oriented facing down or facing up, you really got to make sure that you're looking at pure intercept form before you start making any assumptions about how the parabola is oriented. The rest of this stuff, you can extract your zeros, your roots, your x-intercepts, your coordinates of the y-intercept. You can extract all of that from a factored form quadratic, but you do, like I said, have to be a little bit careful about some of the stuff you're extracting. Down at the bottom, converting from intercept form to other forms, we already talked about how we find the vertex from intercept form. So converting to vertex form to see the vertex probably shouldn't be necessary. If you want to convert to standard form, well, that's a process we all know and love and have been dealing with probably since, I don't know, 6th or 7th grade, foiling, which we are going to talk about at the top of the next page. So how do we multiply binomials? Binomials just something made up of two terms that are added or subtracted, like a lot of the stuff that we've been dealing with, 2x plus 1 and x minus 3, that's two binomials. When we want to multiply two binomials, we use a process that we know as FOIL. And FOIL stands for first, outer, inner, last, and that acronym sort of just tells us what we have to multiply at each step. We first multiply the first terms, a and c, those are the first terms in each binomial. Then we multiply the outer, that's the O in FOIL, the outer terms, the a and the d, those are the outer terms in the two binomials. Then the inner terms, that's the I in FOIL, and then the last terms, the two terms that are last in each binomial. And in that way, we end up with our product of the two binomials. So in order to do 2x minus 4 times x plus 3, first terms, so that is the f, so that's 2x squared. You should probably pause the video and run through this on your own really quickly. I'm sure most of you know how to do this process. So 2x times x is 2x squared. 2x times 3, those are the outer terms, that's going to be positive 6x. Negative 4 times x, that's minus 4x. And negative 4 times positive 3, that's negative 12. Of course, we can combine, as we often can, these two terms in the middle. 6x and negative 4x are like terms, and therefore we can combine them as 2x. So we get, finally, 2x squared plus 2x minus 12. Could we factor out a 2 here? Yes, we could. I'm not going to do that right now. It's not really necessary in the context of what we're doing here. Do recall that if you have a number out here outside of your parentheses, you would have to distribute that number through, or you may have to, I should say. You may have to distribute that number through to all of your terms in order to find out what your A, your B, and your C are. So in terms of some examples, let's go ahead and do example 27, but of course I would run through these on your own. This should not be difficult. This should all be review for the vast majority of sophomores, juniors, and definitely seniors. So in 27A, what am I going to do here? I'm going to ignore the negative for now. I'm going to do x times 2x. So here's what I'm going to do. I'll put the negative, so I guess I'm not ignoring the negative. I just want to keep track of it so I don't lose track of it. So negative x times 2x is 2x squared. X times negative 5 is minus 5x. Inner terms, negative 4 times 2x is negative 8x. And of course, last terms, negative 4 times negative 5 is positive 20. Combining those two inner terms, I get negative, so 2x squared minus 13x plus 20. And I am going to now distribute that negative to each of these terms. So I get negative 2x squared plus 13x minus 20. So negative 2x squared plus 13x minus 20. And I can now see that my a is negative 2, my b is 13, and my c is negative 20. Being able to recognize that your coefficient in front of the x squared is the a, and coefficient in front of the x to the first term, the linear term, is the b, and then your constant out here is the c, will become important on certain questions, especially the matchup questions that we're about to talk about. In 27b, some of you may notice right off the bat that this looks like a difference of squares factored, and indeed when we FOIL this out, we get 4x squared minus 2x plus 2x and minus, oops, went a little too far there, minus 1, and of course the two middle terms cancel each other out, and we do end up with a difference of squares. In example C here, we're going to do 2x times 3x, which is 6x squared. 2x times 2y is positive 4xy. Then we have a negative 3y cubed and a 3x. So what is that? That is negative 9xy cubed. And then the last terms here, negative 3y cubed times 2y. Let me be careful here. So this is negative 6y to the fourth. And this is one of those cases where we don't have any like terms. There's an xy, an xy cubed, a y to the fourth. Yeah, so there's no like terms here. So actually we end up with 4 separate terms in this case. 6x squared plus 4xy minus 9xy cubed minus 6y squared. So that is the process of foiling. Again, hopefully that was just review for the vast majority of you. Down at the bottom of this page, we have to talk about matchups. Matchups really just deal with questions on which we need to identify the coefficients and constants from standard form, although do keep in mind that A is part of intercept and vertex form as well. We tend to talk about A, B, and C, though, most commonly in the context of ax squared plus bx plus c, and I just mentioned this. There is your A, which is the coefficient in front of your quadratic term. There's your B, the coefficient in front of the linear term, and there's your C, the constant that hangs out there at the end. In example 28, this one should be very simple. I would try this one on your own. We just have to look at these quadratic polynomials, and we need to determine the values of A, B, and C. This should be, again, pretty simple. So A in Roman numeral 1 here is 1, B is 2, and C is negative 2. You have your A, you have your B, and you have your C. In Roman numeral 2 here, I'm just going to quickly rearrange these two terms, and then just for clarity's sake, I'm going to write this like this, but I'm going to make that look more like an X. And now I should be able to see I've got my A, I've got my B, I've got my C. So I have 3, 0, and negative 5. This is not a trinomial, of course, this is a binomial. And in this binomial, of course, we don't have our linear term because that linear term's coefficient is 0, and therefore we're not writing that middle bx or linear term. In Roman numeral 3, this is one of those cases where I have to be careful to distribute that number outside the parentheses before I determine what my A, my B, and my C value are. So this is going to be 6x squared minus 3x, and again, for clarity's sake, I'm going to write that plus 0. My constant term is a 0, which is why it's not written over here. So I have a 6 a -3, and a 0. So those are just 3 quick examples that allow us to very simply and easily, hopefully, identify our A, B, and C values. But where matchups get a little bit trickier is in cases like examples 29 and 30, where it's not necessarily so obvious right away what our A, our B, and our C values are. When you see, I'm going to actually write down a little tip-off clue. When you see an equation in which you have standard form on one side of an equal sign, and you have factored or intercept form, so let's say you have x plus or minus some number, and another x plus or minus some number. So when you have standard form set equal to intercept form or factored form, like you do in example 29 or in example 30, usually that means that you are dealing with a matchup, and the process is usually to FOIL the factored side. Usually that's what we want to do. We want to FOIL out the factored side, and then after we FOIL out the factored side and result in another standard form equation, or expression I should say, because that's what FOILing factored form does, is it gives us a standard form expression, we can start matching up our coefficients and constants on the right to our coefficients and constants on the left. Let's take a look at example 29. If you are feeling fairly bold and fairly confident about this, you can obviously try number 29 on your own. If t is a constant and x plus t squared equals blah, 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 what is the value of t? So here's what I'm going to do. First of all, I'm going to point out that we do have that tip-off clue, factored form on one side, standard form on another. So as I said, I'm going to FOIL out that factored side. So I'm actually going to write down my 2 factors here. I don't want to make any careless mistakes. So I'm going to write out the 2 factors. I'm going to bring down the standard form side as well. So what do I get? I get x squared, first terms, xt. However, I'm not going to write xt. I'm actually going to write tx. A lot of students do get into a little bit of trouble when they write xt. If you write xt, it's not wrong. xt and tx are exactly the same as each other because of the commutative property of multiplication. However, I want to keep the x second just because that's the way we tend to write quadratic polynomials, quadratic trinomials. We have a coefficient in front of the x, and then we have the x itself. In order to make it easier for me to see what's going on here, I want to keep the x second and then its coefficients to the left in front of it. So I'm going to do plus tx, then plus another, inner terms, plus another tx, and then plus, last terms would be t squared, and that equals x squared plus 8x plus t squared. And then combining like terms on the left, I have x squared plus 2tx, right? A tx plus another tx is 2 tx's, and plus t squared equals x squared plus 8x plus t squared. So it should be pretty clear that, I've got my x squared here matching up to my x squared here. I've got my t squared here matching up to my t squared here. Well, the final part of this matchup is to look at the bx term on the left and the bx term on the right, and either set those 2 terms equal to each other. In other words, I could do 2tx equals 8x, divide through by x, and get 2t equals 8. However, I didn't really need to include the x's there. That was a little bit of an extraneous step because I know that on the left-hand side of my equation, the 2t is in the b position, the coefficient of x position, and on the right, the positive 8 is in the b position. So I could have just gone right to 2t equals 8. I know that the coefficient in front of x on the left has to equal the coefficient in front of the x on the right. 2t equals 8, divide by 2, I get t equals 4. The question was asking me for t. My answer is 4. T equals 4. Next, I have example 30. If you want to try this one on your own, pause the video and do so. Very similar to the previous question, I've got x minus r squared. That's a factored form. Quadratic equals x squared minus 16x plus m. That's a standard form quadratic, so factored equal to standard form. They want the sum of m and r. Because I have that tip-off clue here, factored equals standard, I'm going to go ahead and FOIL out the factored side just as I did on the previous example. So what I get over there on the left is x squared minus Rx. Remember, I'm keeping the x second here, minus another Rx. So that's x squared minus Rx minus another Rx, and then plus R squared equals x squared minus 16x plus m. Combining those two middle terms, I'm going to do that over here. So that's x squared minus 2rx plus r squared equals x squared minus 16x plus m. Running out of room there. So again, I've got the x squared and x squared, right? There's a 1 there and a 1 there. They all match up. The r squared and the m are going to match up. And now these two middle terms, I can see in the b position, I have a negative 2r on the left, and in the b position, a negative 16 on the right. So that means that negative 2r equals negative 16 divided by negative 2 divided by negative 2. I get that r equals 8. So I now have my r value. I need to add to that r value the m value. How do I find m? Well, I just use my other matchup. I know that this r squared term and this m term have to equal each other. So if r squared is m, and I already know that r is 8, I just do 8 squared. That's r squared. 8 squared equals m, which means that m equals 64. I now have the other value I need, 64 plus 8. Without a calculator, I have to do this. That shouldn't be too bad. That's going to be 72. Sum mr 72. Yes, that's what I was being asked for here. So that's how we do matchups. Some of the matchups you will run into on the test will be even more advanced than these, but the general process is the same. FOIL out the factored side, converting to standard form, and then start matching up your coefficients and constants. So that is how we extract information from and play around with intercept form, and we will move on to vertex form.